All right, so in this example, we're just going to review Riemann sums. We're going to talk about left-hand and right-hand Riemann sums. So we're given a car that's traveling with increasing velocity, and all we know about it is some data that somebody has collected, and it looks like the data was collected every 2 seconds. And we're asked to estimate how far the car traveled during this time. So the first thing I'm going to do is just plot this data. All right, so then we get the data plotted, and then, so how are we going to estimate how far this car traveled? Well, there's a couple different ways, actually more than a couple different ways, but I'm going to tell you about a couple different ways that we could estimate this. The one way that we could estimate is just assume that, just draw rectangles, right? Now I could assume that this 20 feet per second that we started out at just continues until the next data point, and it suddenly jumps up to 30 feet per second. And then I can look at the rectangle that is formed. And if I take all of these rectangles and add up their areas, that's one way that I could get an estimate for the distance that we're traveling. Okay? And that's called a left-hand sum. And it's because we call it a left-hand sum because we're using the left-hand data point in any given subinterval. All right, so we've got this interval from t equals 0 to t equals 10 seconds, right? And it's been broken up into basically 5 different intervals, right? We got 6 data points, but we have 5 intervals, right? If I break it into 2-second intervals, right? So our delta t is equal to 2, and n is equal to 5. N is the number of intervals. Okay, so I can draw all of these little rectangles that represent the left-hand sum and then find the area, right? So let me finish doing that. Okay, so there's a bunch of rectangles, and all we have to do, just like the problem we had before, we just need to find the area to get the distance. So so we're gonna call this the left-hand sum. Okay, it's the left-hand Riemann sum. And essentially we're just going to take the height of the rectangle, right? And so we're going to take 20 times the width of the rectangle, which is 2 seconds. Okay, and we're just going to add up all the areas of these rectangles. So the next one is 30 times 2, right? And then we're going to add, the next one is 38 times 2. And the next one is 44 times 2. Okay. And last one is 48 times 2. Okay, you can put that all in your calculator. But I prefer to actually factor out that too. So, if I'm doing Riemann sums, essentially what I'm going to do is just take all those data points, 20 plus 30 plus 38 plus 44 plus 48, right? I'm just basically adding the first 5 values for velocity and then taking it times 2. I just find that's easier. I wrote it all out so you can see clearly what I'm doing, but I prefer just to add up all of the velocity values and take it times the width of the interval. So that's the way I would put it into my calculator. So I get 360 feet. Okay. Now you can tell by looking at the graph that that's an underestimate. That's less. We don't really know what's going on in here. This function, but the actual curve looks like I've just drawn it as a continuous smooth function. I guess it does say that it's increasing, so which is obvious, but we're not like we don't. What that's saying is that we don't suddenly have these dips. Okay, so that's not the case. So we have an increasing function, and but you can tell that left-hand sum is going to be an underestimate. So I'm just going to write that down. Underestimate of whatever the actual distance was. Okay, now there's another way that we can estimate the distance. Is we could assume that we're going to use the right-hand data point for the area of the rectangle. Okay, so we assume we are at 20, and then suddenly we jumped to 30, and then we went for 30 for the first 2 seconds. All right, and then over the next 2 seconds, we were going 30, and then we suddenly jumped to 38. Okay, so in order to get the right-hand sum, the right-hand Riemann sum, we're going to use the right-hand data points. Okay, and then add up those rectangles. Okay, now these rectangles, continue on down. But I don't know if I'm going to take the time to do all those rectangles, but you get the idea. We're just taking a different set of rectangles. So let me scroll down here a bit and see if I need a little more room to write. Okay, so here's our right-hand sum. I'll just write it in red since I drew it in red. So our right-hand Riemann sum. Okay. Now again, I'm gonna write it all out, so that you see the rectangles, the height, I'm taking the height times the width, right? So, but in this case, I'm gonna start at 30. So I'm basically taking those last 5 values, okay, times 2, right? And then the next rectangle is going to be 38 times 2 plus 44 times 2 plus 48 times 2, and then plus 50 times 2. Okay, now again, I'm just writing that all out just to show you that what I'm doing is adding, I'm multiplying height times width to get areas of rectangles. But if I was going to calculate this, I would just take 30 plus 38 plus 44 plus 48 plus 50, and then take it times 2. So basically what I'm going to do is factor the 2 out. I'm going to add up all my velocity values and take it times 2. It's just easier to put it in the calculator that way. So when I put that into the calculator, I get 420 feet. Okay. Now, just by looking at the graph, you can see that is going to be too high, right? That's an overestimate. So let me write that down. Overestimate. Right? Because if I'm using the right-hand data point and it's an increasing function, that right-hand data point is always greater than the left-hand data point, right? So this is going to be an overestimate of the distance traveled. Okay. So so we have a couple of estimates. Now we could average those. Okay, we're going to get into that later. But what I want to look at here before we leave this problem is the error involved. And I'm going to actually scroll back down so I want to see the, let's see if I can scroll it part way here. All right, so can't see the problem statement, but I can at least see the graph and I can see the calculations. All right, let's look at the error. So the actual, if I look at this first 2-second interval, the actual velocity is somewhere in between this red line and the green lines, right? So what I can do, the error band essentially is made up of these rectangles, right? So I'm just copying what I've done over here is just copy that rectangle. If I stack up all of those error bands, so let me draw that next error band here. All right, then we have another one here, trying to draw them the same width, but actually just draw the column. I'll just draw the whole column. All right, this is really getting messy. All right, but so you can see we've got, I need 1, 2, 3, 4, 5. All right, so what I'm doing is just stacking up this error. So the error band is like this region right here, and it corresponds to this rectangle right here. Okay, so I'm stacking up all those error bands, and the error, which is going to be the difference between the maximum and minimum value, the underestimate and the lower estimate, is just basically the width, which is delta t, right, times, right, the difference between the first value, right, at t equals 0, and the last value here at t equals 10. Okay, and so the difference, there's a 30 feet per second difference. So the height of this rectangle is 30, and the width is 2. So you can see that our error is essentially 60 feet. And you can also see it down here. If I take the difference between these two values, it's 60 feet. Okay, so the difference between our overestimate and our underestimate is 60 feet. Okay, so I'm going to let you take a look at this next problem, example 3. It's essentially the same problem, except that now we have more sampling. We have velocity taken every 1 second and rather than every 2 seconds. So I want you to try this out. Try coming up with the upper estimate and the lower estimate, the underestimate, I guess under and over estimates using the left and right hand sums.